Grandón has a lot of expertise in things like HSC. She's going to tell us about impact of baryons and cosmological parameters from weak lensing and non-Gaussian statistics. Cool.
Okay, thank you. Thank you to the organizers and the audience and this amazing venue. Okay, so I'm going to talk to you about non-Gaussian statistics. These are estimators of the lensing field. The idea is to improve our precision on cosmological parameters, but also check on the accuracies of our constraints when we have a modeled systematic effects. So, very quickly, yes, okay. Weak lensing, okay, I think you're all familiar with the lensing mechanism. So basically, weak lensing is the special case where we have tiny distortions of our galaxy shapes. And in cosmology, this deflection of light is due to the large-scale structure. So weak lensing is a very powerful tool because it's sensitive to the total matter distribution. So we can characterize this distortion of galaxy shapes by three quantities: convergence and the two shear components. So convergence are basically magnifications, increasing the size or decreasing the size of the galaxy shape, and the shear are this anisotropic stretching in the galaxy shape. And in my research and the work I'm going to present, I focus on the convergence. So convergence is described basically by this integration along the line of sight. And as you can see here, it depends on the density contrast. So this is how it traces the matter distribution. And here you have like an example of how this galaxy shape is distorted. And basically depends on some geometric factors, the lens efficiency. The important part is that with convergence, we can trace the matter distribution and obtain these projected mass maps or convergence maps of the lensing field. So here, this is the data, the weak lensing data I'm implementing in my research, and the standard approach is to measure the power spectrum, the weak lensing power spectrum, which depends on the matter power spectrum. So you can see that in this way, we can constrain cosmological parameters with the weak lensing power spectrum. But I want to go beyond that. So here I have three maps. Two are Gaussian fields, and one is a non-Gaussian field. And I think you can see by eye. You should never trust things by eye. But in this particular example, you can see by eye there's more structure in our maps, in the non-Gaussian map. But if I now compute power spectrum on each of these maps, I obtain roughly the same. So this means if I want to extract all the information contained in the lensing field, I need to go beyond power spectrum or two-point function. So this is why non-Gaussian statistics are being more and more popular for weak lensing surveys. And you have a long list of non-Gaussian statistics. There's a poster you can see of different non-Gaussian statistics for modified gravity. There's a talk later, I think, on other non-Gaussian statistics. I'm going to focus on three in my talk. So first, I have the peak counts. This is a very easy statistic because you basically have these convergence maps and you measure the local maxima in the maps. So you basically are tracing the massive halos in your line of sight, but also you can trace other regions like projection of smaller halos. But we can complement the peak counts with the minima, which is basically tracing underdense regions and voids in our mass maps or convergence maps. And finally, I also compute the PDF, which is basically a histogram of the convergence or pixels values of our maps. So these are three non-Gaussian statistics, so are very powerful, super easy to compute, and I'm going to show you that this can provide very good and improved cosmological constraints compared to power spectrum alone. So first, I'm going to focus on HSC Y1 data. I designed a pipeline with embodied simulations, so I tried these different non-Gaussian statistics with mock data and with real data. So let's focus on mock data first. So this is more or less how the maps look like for different smoothing scales. So basically what you do is you apply a Gaussian kernel that removes small structures and exploit different features of the map. So you have 2 arcmin smoothing scales. We see the small structures in our map. And with the 8 arcmin, for example, we now can see better the massive structures. We remove non-Gaussian information, but also can help us to determine what is the impact of systematics. So it's very good to have different smoothing scales. And why HSC? HSC is actually the camera, Hyper Suprime-Cam, is considered a precursor of LSST. So it's very good to try and test different systematics in order to design future pipelines for LSST. So in the red regions, here you can see what is the HSC footprint compared to KITS and DES. It's a smaller footprint. It covers a smaller area of the sky, but it goes deep. And here you can see what are how the statistics look like. So this is the PDF first, the peak counts and the minima, and how they vary when we vary the S8 parameter. So I want to constrain S8, and from here you can already see that they are sensitive to S8. If we decrease the value of S8, we basically are modifying mainly this region here and the tails of our statistics. And in a tomographic analysis, we can also see that different redshift beams react to these cosmological parameters differently. So it's always good to have also tomographic analysis. Okay, so these three statistics, and now I implement an MCMC inference with the MOX data. And here you can see what is the improvement in precision of our cosmological constraints. So this is power spectrum in green. Then we have minima in gray, peaks, and PDF. So PDF is the one based on this analysis which gives us the best constraining power. So that's great. We have better precision. It's more or less 35% for these analysis choices. But now I wonder what would be the impact of systematics. So, okay, we have precise constraints, but how biased they could be when we include different systematic effects. And one very important systematic for stage 4 LSST or Euclid is baryonic feedback. So basically, baryonic feedback is just a bunch of astrophysical phenomena that reshape the distribution of gas inside halos, and that modifies the gravitational potentials. So here what you can see is different hydrodynamic simulations. They implement baryonic feedback with different parameters, different calibration methods. And this is the power spectrum based on these simulations with baryons and without baryons. So there's a general trend. All the different simulations have a suppression on the power spectrum. But what is important here is that there's a disagreement on the amplitude of this effect and also at the scales at which this effect is important. So therefore, baryonic feedback is a huge challenge for power spectrum, but it's even more difficult for non-Gaussian statistics. So what I do now is analyze HSC Y1 MOC data and understand what is the impact of baryons for these non-Gaussian statistics. So these are different hydrodynamic simulations. They vary different, they focus on different astrophysical phenomena. And Bahamas, for example, here they vary the AGN heating temperature. This is a parameter of the simulation. And what you see here is, okay, first we have this gray shaded region, which is the HSC Y1 uncertainty, 1 sigma, and the impact of baryons on the different statistics. So the PDF here computed in maps with baryons over maps without baryons, and the same for the peaks and the minima. And you can see that there's an impact of 10% more or less, but it's everything inside the 1 sigma region. But we could have off-diagonal terms in the covariance, so we proceed with propagating this impact on cosmological parameters. And we want to investigate what is the impact specifically on S8. So the horizontal axis is the difference between S8 based on the analysis with baryons and without baryons. H stands for hydrodynamics with baryons. And we have different baryonic feedback models. So this is the first baryonic feedback model, Bahamas, high AGM, with different smoothing scales. So 2 arcmin is the smallest scales in this analysis. And you can see that the biases due to baryons for S8 are 1 sigma or less than 1 sigma for PDF and P counts. And as we add different baryonic feedback models, we see that this bias is, there's no bias basically. So if the universe behaves like Bahamas HGN, like this is the baryonic feedback that represents what universes look like, then we could have these kind of biases in our SI values. So if we want to investigate tensions, this is very important. And this is TNG. TNG is very similar to low AGN. And this, well, the PDF and the peak counts are the most impacted, but this is reasonable because they have better precision. Okay, and now let's replace the data vector by real data. So what is the result of HSC Y1 real data for the non-Gaussian estimators? So here is Planck results, and here you have the different non-Gaussian statistics for the different scales. And basically, we find no tension with Planck. And interestingly, we don't see any shifts in S8 when we include the small scale. So basically, baryons are not that important in real data, or there's other scale-dependent systematic effect that is having a more important impact. So that's lesson learned. This is also consistent with other HSC Y1 results. And we find no tension. But okay, what happened with LSST or Euclid? Because this is almost 1 sigma for PDF peak counts for HSC Y1. But we have better precision with LSST and Euclid. So our results indicate that for peak counts, for example, for different smoothing scales, now the impact of baryons is more important. So the standard strategy that we can implement is to remove, for example, these points, because we know the impact of baryons is important and goes beyond 1 sigma. But then we are removing information. We have money for exploiting small scales, extract all the information in our data, and we are just throwing away data points. The idea is to keep all data points. So, but this is a problem, right? So then we could do is just go to larger smoothing scales and see at what point we can have unbiased results. And this is the forecast of what is the impact of baryons for LSST. So this is the dark matter only results. So this is, you have to compute bias respect to this dashed line, and we can see it's huge biases. So for LSST, this is going to be a problem based on this forecast for these different baryonic feedback models. And if we increase the smoothing scales of our maps, we can recover more or less the true cosmology. We are not that biased, but we are losing precision. So this is the question, how we account for this baryonic feedback uncertainty biases in our cosmological analysis of non-Gaussian statistics. And this is the last part of my talk. I'm proposing a Bayesian framework for the non-Gaussian statistics, and this is called Bayesian model averaging. It basically states that we have a model uncertainty, right? We don't know which one is the correct model of baryonic feedback. There's a large discrepancy. So what we could do is the data decide which one is the model that reproduces reality better. How can we do that? We combine our posterior distributions. So this is the posterior, the samples you obtain from your inference of your cosmological parameters given some specific model that you choose. And then you weight this average by the Bayesian evidence. So you let the Bayesian evidence rank the relative probabilities of your models to have generated the data. So basically, you have to run this for each of the cosmological models, and the model with larger evidence is the one that is preferred by the data. But we also propagate the uncertainty that we are not sure which of the theoretical models we have here is the one that reproduces the reality, how the baryonic feedback acts in the universe. So let me show you just preliminary results. This is an analysis with the peak counts for LSST. I'm using this likelihood as a matter. And how we account for the baryonic feedback in the inference, we basically inject a correction factor of baryonic feedback in the modeling. So this is obtained for different baryonic feedback models. And I consider 2 cases. So now I have a data vector contaminated with baryons, and now my theory is also contaminated with baryons. And basically, for example, if I run an analysis for the different models, And my data vector, I know this is like a consistency test. I know it's a fit AGM model, for example. The posterior that obtained from the Bayesian model average gives more weight to the right model, right? Because I know that fit AGN is the right model. But we can have other situations that none of these models really reproduce reality, and that case is called model misspecification. So none of the models I'm trying generate the data I'm observing. So in that case, I consider like a fake baryonic feedback correction based on combination of two models. And the result is basically that I obtain unbiased results, but the price I have to pay is still a loss of precision. So basically, the idea is to combine as many models as I have in order to obtain precise cosmological constraints and unbiased results. So then we can investigate if these tensions come from systematics or come from new physics. So this is my conclusions. Basically, HSC Y1, no tension with Planck based on year 1 data release. And the non-Gaussian statistics are powerful tools. They obtain precise constraints. And we need to investigate what is the impact of systematics. Because if we are biased, there's no point in having smaller error bars on our parameters. And yes, so systematics, I think, is the problem based on yesterday and today. OK, thank you.
That was fantastic, and thank you for keeping time. All right, do we have questions?
Thank you for the nice talk. I have a few questions, but maybe I'll just start here. So how do you do the measurements that you were showing how the statistics change? Do you measure it directly from the simulations, or did you do this correction on like some embodied simulation and then?
OK, so the statistics are obtained from embodied simulations for the inference pipeline. And for the correction factor of the baryons, if that's what you mean, I obtained from TNG and...
No, I mean the plots you were showing earlier. You showed these ones. Yeah.
Yes, so this is also Bahamas. And here I use SLICs and CosmoSLICs to model the statistics.
OK, so you're not measuring directly from Bahamas then?
Yes, for the correction factor, yes.
OK, so you just measure the correction factor, but the dark matter only, and then add that to the dark matter only one.
So the dark matter only data vector is from SLICs or CosmoSLICs, doesn't matter. But then I measured the, for example, P counts in Bahamas high AGN, and Bahamas provides you the dark matter only counterpart. So then I obtain this correction factor.
OK, so this is the correction factor.
Yes, exactly. This is the correction the fractional difference, basically.
And then another question. So you showed that S8 is smaller when you have AGN feedback or hydrodynamic.
Yeah.
You have baryon feedback. Is this because your main signal comes from this middle bit where kappa is small?
Sorry?
So you have a suppression when kappa is large.
Yes. In the mock data analysis, you mean here.
No, the same plots, if you look at the plots.
So the LSST is different because in order to illustrate the Bayesian model average, I inject the variance in the model, not in the data vector. So if I inject it in the data vector, this all shifts to lower SA values.
Yes, yes.
Exactly.
I'm just asking, why does S8 get smaller when you have baryon feedback? Because with power spectrum, you know, it gets larger because you have suppression of power.
Yeah.
And in your plots, I can see that there's only one place where you get a boost.
Yeah. So, okay. So this is how the statistics change with S8. So you can see that, I don't know if it's clear. So for example, here in the tails of the P counts or PDF, when you have a suppression of the tails, then you obtain a smaller S8. And that's what we obtain in the mock data analysis. Why is that? Well, for example, in this region of peaks, basically, for example, AGM feedback removes the gas from the inner region of the halo, and that basically impacts how we have less peaks, basically. We have less structure in that regime. And that gas is then, it goes to this region here. So it moves, the gas doesn't disappear, right? It moves now to like not so overdense regions, so intermediate regime, and that's why we now have also an effect in this range.
Okay, thank you.